So in this video, we're going to learn about binomial probability distributions, which are very similar to geometric distributions, but a little bit differently. Hope you pick up on some of the subtle differences here. So this is also called Bernoulli Trials, is the other sort of common name you might hear. And the idea of what we're trying to do is find a formula for the probability of getting exactly x successes, so x number of successes in n trials. So a lot like geometric distributions, the trials have to be independent. So that means independent here means that the two trials, the first trial can't influence your second trial. So whatever happens the first time happens, and then there's exactly the same odds of that happening again in the second trial. It's not influenced by a previous trial. The outcome, the trial outcome, must either be just success or failure. You can't have sort of a tie option or something like that. So the outcome has to be either success or failure, nothing in between. And the p-value is going to be the probability of that success. Probability of a success on a single trial only. So not to be confused with what we're going to call capital P, which is the probability we're solving for here, the probability of getting exactly x successes after doing n trials. Little p here stands for the probability of a success on just one trial, just a single trial. Q is the probability of failure on a single trial. So you can probably guess that if Q is the probability of failure on a single trial, then we can get it by doing just 1 minus P. It's basically not P, or not success is defined as failure here. All right, now figuring out this formula is pretty tricky. So how I thought we'd try this is with a simple example. We'll use this example to kind of develop our equation, and then we'll use it for more interesting things after that. So here's our simple example. We want one success. We only need one success, so that's why I've defined x as 1. We're going to have n be 5 trials. To pick something that has an easy probability, we'll just be rolling a dice. So our trials is 5 times, so we roll the dice 5 times. And our success we've defined as rolling a 1. So the probability of rolling exactly 1 in 5 trials, that's what we're looking for here, and that's what we're trying to sort of develop a formula for. First, I can define P. So P is the probability of a success in just a single trial. So what's the chance that you roll a 1 when you roll a dice 1 time? Well, there's 1, 1, and there's 6 different numbers on your dice. So that probability is 1 in 6. Q, I can also define right off the bat. Q is defined as the probability of failure in a single trial. So you roll a single dice. What's the chance that it's not a 1? Well, that'll be 1 minus a 6th, or 5/6. All right, so we've got P, we've got Q. Now we have to try and create some sort of a formula here. Okay, so we've got 5 trials, and we need one of them to be a success. So one way I might do that is like this. Maybe the first trial is a success, 1 in 6. And then the next trial has to be failure. The next trial has to be failure, and the next trial has to be failure, and the 5th trial also has to be failure. So I have 1, 2, 3, 4, 5 trials. I'm multiplying probabilities each time because these are all and situations. I roll the dice once and twice and 3 times. I roll it 5 times in a row. So that's an and situation. And only one of those is to be a success. So only one is the 1/6. The problem here is that this is kind of like claiming that order matters. And order doesn't actually matter. That's not really what I'm looking for. I don't care if the success is the first one or the third one or the 4th one. So there's more that I'm missing out on here. So maybe this is like an or situation, right? This would be one option, but I could also have this option. Maybe the first one is a failure, but the second roll, that's my 1 that I get, and then the rest are failures. 5 out of 6, 5 out of 6 failure, and the last is a failure. Okay. You can kind of see where this is going. There's basically 5 different spots that this 1 out of 6 could be in. So I could find the probability for this one right here. That would be my p here to the power of 1. So see how I have 1 over 6 just to the power of 1 here. And that's being multiplied by q, my probability of not getting what I want. And it's to the power of, looks like 4. But how did I get the 4? That's 5 trials minus 1. Basically, it's everybody else is a failure. So if I have 1 success, everybody else is a failure. Here, notice it's exactly the same formula. So it's still just p to the 1. My 1 over 6 is still just one of them. And I still have q, the 5 over 6, and they're not in the same order, but there's still 4 of them. So it's still to the power of 5 minus 1. That hasn't changed. Notice that we can put this 1 over 6 in 5 different places, and it's an OR situation, so I'll be adding each of these. Adding the same number to itself 5 times, well, that's the same as just multiplying by 5. So that's kind of what I'm doing here. So I could say my formula looks something like 5 times p to the 1, q to the 5 minus 1. So we're close. The thing is, it's a little messier than just the number 5. I mean, what if I was choosing not just 1 success, but maybe 2 successes? Then I'd have to look for all the ways to arrange 2 successes in a group of 5. That sounds a little bit like 5 choose the number of successes, or 5 choose x. Okay, now we need to step back from that and create a general formula out of it. So make a little box because this is going to be important. This is my binomial probability distribution formula, and it is for the probability of exactly x successes in n trials. So we need to go a bit vague. 5 here, that was the number of trials. So I have n, choose, and it was choose 1, but 1 was the number of successes, so that's x. Then we multiply that by our probability of success in a single trial, p, lowercase p. Here it was to the power of 1 because there was only 1 success, the 1 in 6. But had there been 2 successes, I would have multiplied 1 in 6 by 1 in 6, or 1 in 6 squared. So it sounds like I should be putting p to the power of x, however many successes I have. Then I'm multiplying by q here, and q has to kind of fill in all the other spots. So if there was 5 trials, it has to fill in 5 minus x. If there was n trials then, it has to fill in n minus x. So we'll take q and multiply it by itself, n minus x times, so that we'll put that in our exponent. And that right there is our lovely formula for the binomial probability distribution. So let's try using that on a slightly more complicated, but not too complicated one. So here's still a dice. We're going to roll it still 5 times, but this time I want to know the probability of rolling exactly 3 ones. So think about what is x, n, p, and q. First, x. X is the number of successes. Success is rolling a 1, so there are 3 successes. N is the number of trials. The dice is rolled 5 times, so n is 5. P is the probability of success on a single trial. The success is rolling a 1. The probability of rolling a 1 on a single trial is 1 in 6. And Q is the success of failure on a single trial. So the probability of failure on a single trial is 5 in 6, or 1 minus 1 in 6. Now that we know all that, we can plug that into our formula that we've just created for the probability of exactly 3 successes. So x is going to equal 3 in here in n trials. So we have n choose x. In this case, it's 5 trials. And we're looking for 3 successes among them. Then we have a probability of 1 in 6 to the power of x, the number of successes I want, which is 3. And then our probability of failure, not getting a 1, 5 in 6, to the probability of n minus x, so 5 minus 3. All right, toss this all into your calculator. So 5 choose 3. It's going to give us 10 here. 1 in 6 to the power of 3 there is going to be 1 into 16. And 5 in 6 to the power of 2, right, 5 minus 3, is going to be 5 squared, which is 25, over 6 squared, which is 36. Okay, we get to multiply that all out. And we get 0.032. So the probability of getting exactly 3 ones when you roll a dice 5 times is 0.032. All right, now we're ready to graph this, because it's not a distribution until we actually graph it. So here's another example. So Allison is playing soccer, and the probability of her scoring a goal on a single kick is 0.6. She's got a 60% shot because she's really good at soccer. And let's say she has 7 shots on the net during a game. We want to plot a graph here of the probability versus each possible number of scores she could actually get in the game. She might get 7 every single time she hits a kick towards the net. It actually gets in. She might get 0. That'd be really unfortunate. She gets 7 open shots, but none of them go in, or probably more likely somewhere in the middle. So that's what we're going to work out. Let's start out by figuring out x, n, p, and q. Okay, so x is actually variable here. So x could be 0, 1, 2, 3, 4, 5, 6, or 7. So that's actually the thing that we're going to be investigating here. X is the number of scoring goals she gets. So number of successful goals. Successful goals there. I'll just label it at the bottom. So x could be anywhere between 0 and 7. Let's fill that in our little table of values too. X could start at 0, but it's going to go all the way up to 7 is the most goals she could get. We're going to assume that Allison can't get an accidental goal where it just sneaks in there without her actually trying to score. Okay, n. N is the number of trials. In this case, the number of trials is, well, how many times did she get to attempt to score on the net? That's 7 shots on the net. P is the probability of her scoring on a single shot. So that's the chance of success in one kick, and that's 0.6. Q is the probability of failure in a single shot, so that's 1 minus P, 1 minus 0.6, which is equal to 0.4. All right, so I have my nice binomial distribution formula already nicely written out here for us. So it's now just a matter of plugging this into our calculator to fill out each of these probabilities here.